Hi everyone. I hope that you are traveling well. My name is Professor Andrew Timming, and I'm very pleased to welcome you to this lecture associated with my book, Applied Statistics, Business and Management Research. This lecture corresponds to chapter 4 of the book, and this is the second lecture in a 3-lecture series for this chapter. So just a very brief recap of lecture 1 for chapter 4. The previous lecture, we introduced the concept of the normal curve, also commonly referred to as the bell curve. And we talked about some of the, let's say, geographical features of that curve. You'll recall that we explained that the way in which we generalize from a sample to a population using parametric statistical tests is through our knowledge of the geography of that normal curve. We are going to expand a little bit on that concept in the present lecture. So we'll learn a little bit more about the normal curve and the theoretical mechanism that we use to generalize from a sample to a wider population. So in this lecture, we will first look at what are called Z-scores. These are standardized scores that we can use to describe where a data point sits on a normal distribution in relation to the mean. And then we'll look at the central limit theorem, which is the conceptual or theoretical mechanism that we use to enable us to generalize our results from a sample to a population. And lastly, we'll look at the inimitable p-value. The p-value is a statistic that will tell us with a certain degree of certainty whether or not we can generalize our results to the population. Okay, just to recap, this is the textbook that we're using in this lecture series, Applied Statistics, Business and Management Research, which I wrote recently and published through Sage Publications. You are welcome to purchase this book if you'd like, or you can check it out at your local university library. Either way, I hope you enjoy reading it. Let's talk a bit about what a Z-score is. Sometimes this is referred to as a Z-score. If you are in the UK or in Australia, in the United States and Canada, this would be referred to as a Z-score. So when I was learning statistics, struggled to grasp. I could calculate a Z-score, as we'll learn about in the next slide, but I struggled to grasp the meaning of a Z-score and how it related to the raw data. So let me just take a few moments to try and explain this as best I can. First point you need to understand is that in statistics, there are two different ways that you can express the same score in a distribution. Also, you could argue there are two different ways you can express a relationship between two variables, but that's getting ahead of ourselves. So first there's the raw score, which is the unstandardized score. This is the actual score, what the data tells you. But every raw score has a corresponding Z-score, and the Z-score is a standardized score. So what I'm saying is that if you have a variable and a set of data points within that variable, let's say age, for example, that means that every single raw score, every single age in that variable can be expressed as a raw score, as an unstandardized score, but can also be expressed as a Z-score, which is standardized, right? So the Z-score is essentially a mathematical conversion of an unstandardized raw score into standard deviation units. Okay, so let me explain what I mean here. A Z-score of 0 is always the mean of a distribution in an ordinal or scale variable. So whatever that mean is, if it's age, the mean might be 42 or something like that. Then a mean of 42 always corresponds to a z-score of 0, which is the mean. Or if you're dealing with an ordinal variable and the mean is, say, 2.7, then 2.7 as a raw score always corresponds to a z-score of 0. A z-score of 1 corresponds equivalently to a raw score that is exactly 1 standard deviation above the mean, whatever that number is. And a z-score of -1 corresponds exactly to a raw score that is 1 standard deviation below the mean. And a z-score of -2 is exactly a raw score that is 2 standard deviations below the mean. And a z-score of 2 is corresponding to a raw score that is 2 standard deviations above the mean. So it's a little bit complex, but let's see if we can calculate a few of these numbers and it might make more sense. So here we have the equation that we use to calculate a z-score. And it's a fairly simple equation, even if it looks a bit scary. It's actually quite easy to implement. So to calculate a z, you simply take xi, which is a raw unstandardized score, so an individual score within that particular variable, and then you subtract the mean of that distribution of scores, and then you divide that by the standard deviation. So obviously, in order to carry out this calculation, you first need to calculate the mean of the distribution of scores as well as the standard deviation, which we talked about in the previous lecture series. All right, let's calculate a few z-scores for your benefit. As I said, it's fairly easy using the equation on the previous slide. So what I'd like you to do is I have 1, 2, 3, 4, I have 5 different scores here. These are IQ scores, so hypothetical IQ scores. And these are the raw or unstandardized IQ scores. And what I'd like you to do is to use the previous equation to convert these raw unstandardized scores into standardized z-scores. So in order to do this, we need 2 pieces of information. First, we have the mean, which is 100. That's a typical mean in IQ. And the standard deviation, which is 15. So I'd like you to pause it now, if you will, and try and calculate these. But if you're very restless, I can just walk you through these now. So starting with employee A, we have an IQ of 107. So we can already tell that this is a number that's slightly above the mean. It'll be a positive number, therefore. To calculate this, we take 107 minus 100, and then we divide that by 15, and that gives you a z-score of 0.47. So a raw score of 107 is a z-score of 0.47. Bear in mind that a z-score of 1 is 1 standard deviation above the mean, so this is roughly half a standard deviation above. Next IQ score is 92, so we take 92 minus 100 divided by 15. This will give us a negative score, we know, because 92 is less than 100, which is the mean. So in this case, our z-score is negative 0.53. So pretty close to 107, but just on the other side of the distribution. Next one, we have a pretty high IQ score here, 131. To calculate the z-score, we take 131 minus 100 divided by 15. That gives us a z-score of 2.07. So what this means is that a raw unstandardized score of 131 corresponds to a score that's roughly 2.7 standard deviations above the mean. Next one, we have 95. So we know this is going to be a negative number. Take 95 minus 100 divided by 15. That gives you minus 0.33. So this is the closest one to the mean to 0 as possible. And lastly, we have a really high IQ score. This is 158. So to calculate the z-score, we take 158 minus 100 divided by 15, and we get a z of 3.87. So this is almost 4 standard deviations. Very, very high. 4 standard deviations almost above the mean of 100. So hopefully that gives you a sense of not only how to calculate a z-score, but also how to interpret them. So what we want to do in inferential statistics is to make a quantum leap, or what I've called a quantum leap, from the data in our sample to the wider population from which the sample was drawn. Now, as I've said before, ideally, it would be great if we could analyze population data. In other words, if we had census data for every question that we wanted answered, it would be fantastic, because then we wouldn't need to use inferential statistics. Whatever relationship we found would be the reality of that relationship in that population. But usually populations are very large, so it's not feasible due to the costs and the time associated with data collection to administer a questionnaire to everyone in a population. This is especially true if your population is a country, for example. If your population is a company, it may be possible to get data from everyone, but even that is difficult to do because there will always be people who are reluctant to fill out surveys. So the next best thing is to collect data from a random sample of individuals drawn from that population. And remember, a random sample is defined as a sample where everyone in the population has an equal probability of selection into that sample, all right? So let's think about what we know and don't know here. We have data from a sample, whatever sample size that might be. It might be 100 employees, it might be 1,000 individuals, or whatever. So we have sample data, and these data are known. We don't have population data. The population data are unknown. So what we need to do is try and estimate population data based on the known data in our sample. So what we're doing is we're estimating population parameters based on probability theory. Now, you might be asking yourself, well, if we don't know population data and we do know sample data, how are we going to accurately generalize from our sample to our population? What is the mechanism that we can use to make those generalizations? And the mechanism is exactly what you have in front of you. It's called the central limit theorem. And it is a very important theorem in statistics. In fact, when I was an undergraduate student, I had to memorize this theorem. That's how important it was. But I'm not going to make you do that, unless you want to, of course. So the central limit theorem is based on what we refer to as the sampling distribution of sample means, right? And this is a theoretical tool that allows us to assume with a certain degree of confidence that our sample results generalize to the broader population from which the sample was drawn, right? So this is the actual central limit theorem. I'm going to read it word for word because it's so important. If repeated random samples of size n are drawn from any population with an unknown mean of mu and a standard deviation of sigma, then as n becomes large, the theoretical sampling distribution of sample means will approach normality with a mean of mu and a standard deviation of sigma divided by the square root of n. All right, that's a bit complex, but what it's saying here is that if you were to take an infinite number of samples from a population, if you say you had a population of 5,000 and you took an infinite number of samples of 100 individuals from that 5,000, each sample might be slightly different in terms of how it looks, right? How the distributions appear. And that makes sense because every sample, even if it's randomly drawn, there's still the possibility that it won't look and behave exactly like the population. And that can be problematic if you draw a sample that doesn't look and behave like the population and try and make a generalization. But what this theory is saying is that if you take an infinite number of those samples, then over time, your distributions will appear roughly normal. And because they will appear roughly normal, they will be predictable. So that's why in the previous lecture we talked about the geography of the normal curve and how important it is to understand that geography. So based on the logic that I just explained to you surrounding the central limit theorem and the mechanism that we use to generalize from a sample to a population, what you will do in every inferential statistical test that you carry out, not only in this class, but beyond this class as well, is you will have, first of all, your result. So let's say, what is the relationship between X and Y in your sample? That's your result, whatever that is. But then attached to your result will be a second number, a second statistic called a p-value. And this is a really important concept. It's probably the core concept in inferential statistics, so absolutely essential that you understand it. So a p-value is what we refer to as a probability value. It's the statistic that accompanies your result, and we use this statistic to estimate the probability or the likelihood that the results from our sample generalize accurately to the wider population. So we have a generally agreed upon cutoff for p-values, and the cutoff is 0.05. So a p-value is always going to be a number between 0 and 1. It can't be less than 0, it can't be greater than 1. And what we've agreed on as data scientists is that if your p-value associated with your result is lower than 0.05, then we conclude that the result in our sample generalizes accurately enough to the wider population. That is to say that this result is statistically significant. Another way of saying this is that if your p-value is greater than 0.05 or equal to 0.05, then your result is statistically insignificant. Then the result within our sample is not large enough or not strong enough to generalize to the population, and therefore we conclude that there is no likely relationship or no likely association. So as I said, the p-value is always a number between 0 and 1. And what this number tells us is our degree of tolerance for making an error in generalizing from a sample to a population. So I've given you an example here. If your p-value equals 0.049, so just barely less than the cutoff of 0.05, then essentially if we multiply that by 100, we get a percentage, and that percentage is 4.9%. So what we're saying is that there is a 4.9% chance that our generalization from the sample to the wider population is incorrect. So let's say we carry out 6 statistical tests and we get the results of those tests within our sample. And remember, each result comes with a corresponding p-value. So we have our 6 p-values here. And what these p-values will tell us is whether or not we can generalize that result confidently from the sample to the population. Let's try and interpret these p-values. The first one gives you a p of 0.06. Now this value is above the cutoff of 0.05, and therefore we would conclude that there is no relationship between x and y, or between our variables in this sample, right? In other words, there is a 6% chance, so if you multiply 0.06 by 100, you get a number 6, and that tells us that there's a 6% chance that we would make a mistake in generalizing from the sample to the population, okay? And we've agreed that that is too much of a chance, right? We have to pick a cutoff, and that cutoff is less than 5%. So anything with an error rate of less than 5% we're okay with, but above 5%, that's too much. So the next p-value, 0.01, tells that there would only be a 1% chance of making an error in generalizing from the sample of the population. And this value is below 0.05, and therefore we would conclude that this result is statistically significant. The next p-value is 0.93, so that's clearly above 0.05, very much so. And if we convert that into a percentage, then we would be saying that there's a 93% chance that we would be making an error if we were to generalize the results from our sample to our population. Next one is 0.52. So this would be an indication that this result is not statistically significant, that it is not generalizable, that there's a 52% chance of making an error if we were to generalize. Next one is 0.11. So again, this would be a result that is not statistically significant and therefore not generalizable, and that there would be an 11% chance of making an error if we were to extrapolate from our sample to our population. But the last p-value is very, very low. So clearly it's strongly statistically significant. It's very much below 0.05. And if we were to convert this into a number, multiply 0.001 by 100, then we would say that there's only a 0.1% chance of making a mistake if we were to generalize from the sample to the population. So this is how you interpret p-values. We will certainly be coming back to this concept again and again because it is so core to the concept of inferential statistics. Okay, thank you everyone for your time. Thank you for bearing with me, and I look forward to seeing you at the next lecture. Have a good day, everyone. Bye-bye.